Hello my dear students, I am Dr. Jithender Reddy, working as Senior Assistant Professor in the Department of Mathematics and Management Sciences. In this video, we are going to learn the analytic function. This is one of the important topic in the complex analysis. In this video, first we will discuss what is the definition of the analytic function. Then we will discuss a few properties. Then we have to solve the problems. Coming to the definition of analytic function. A function f of z is said to be analytic function at a point z0 if it should be satisfies two conditions. First one, the function f is differentiable at the point z0 and f is differentiable in the neighborhood of the point z0. Or you want to say a function is analytic, then first we have to check the conditions. First one is the function is differentiable at the particular point and differentiable in the neighborhood of that point, then we can say the function is analytic. Suppose this is a point z0. Neighborhood points are this. The function f of z is differentiable at z0 and differentiable in the surrounding points of the z0, then we can say the function f of z is analytic at that point. Coming to the properties, a function f of z is analytic in a domain if it is analytic at every point of the domain. Suppose I am considering this is a domain D. The function f of z is differentiable as well as analytic at each and every point on the region D, then we can say the function must be differentiable as well as analytic on the domain D. The analytic function is also called as holomorphic or regular or monotonic function. We have the another important definition, that is the entire function. A function is analytic everywhere, then we can call that function as the entire function. Suppose I am writing one function e power z. Everybody know e power z is a continuous everywhere, and its differentiation is also same, e power z. This is exists everywhere in the entire complex plane, so that we can say this function is analytic everywhere, so that we can say this is the entire function. Then coming to the Cauchy-Riemann equations, or you want to check the given function is analytic, then first we have to verify the real and imaginary parts of the functions are satisfying Cauchy-Riemann equations. Then we will check the first order partial derivatives of u and v are continuous. Here we have the statement of the Cauchy-Riemann equation. A function f of z is equal to u of x comma y plus I times of v of x comma y is differentiable at the point z0. Then at this point the first order partial derivatives of u and v, that means real and imaginary parts of the functions derivatives exist and satisfies the Cauchy-Riemann equations. The Cauchy-Riemann equations are dou u by dou x is equal to dou v by dou y, and another one is dou u by dou y is equal to minus dou v by dou x. These are Cauchy-Riemann equations in the Cartesian form. Coming to in the polar form, dou u by dou r is equal to 1 by r into dou v by dou theta, and dou v by dou r is equal to minus 1 by r into dou u by dou theta. These are Cauchy-Riemann equations in polar form. As well as we can denote these Cauchy-Riemann equations in the other form ux, that means dou u by dou x is equal to vy, that is the dou v by dou y. and another one is dou u by dou y, dou u by dou y, this can be written as u suffix y is equal to minus Vx, that means dou v by dou x. The another notation of the Cauchy-Riemann equations, ux is equal to vy, another one is uy is equal to minus vx. The Cauchy-Riemann equations are necessary conditions to check the analytic function. That means the function is analytic or differentiable at the particular point z or z naught, then the real and imaginary parts of the analytic function should be satisfies the Cauchy-Riemann equations. The first order partial derivatives of the real and imaginary parts of the function, that means dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y are continuous, as well as u and v are satisfies Cauchy-Riemann equations, then we can say the function is analytic. Here we have that property, the function f of z is equal to u of x comma y plus I times of v of x comma y is differentiable or analytic on the region D if and only if the first order partial derivatives of u and v are continuous on the region D. That means dou u by dou x, dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. These four derivatives are continuous on the region D, as well as u and v are satisfying the Cauchy-Riemann equations, then we can say the function should be analytic, and as well as we can say differentiable on the region D. Or you want to verify the function is analytic, then first we have to find the real and imaginary parts of the function. After finding the real and imaginary parts of the function, we have to do the first order partial derivatives. The first order partial derivatives are continuous, as well as u and v are satisfies Cauchy-Riemann equations, then we can say the function is analytic. Now we are going to discuss a few problems on the analytic function. Coming to the first function here, z square. Now we are testing, is it analytic function? After that we will check, is it an entire function? Entire function is nothing but the function is analytic everywhere. Now I am writing the solution to the first problem, z square. Let f of z is equal to z square, since z is equal to x plus iy. This is a complex variable in the Cartesian form. Now we are going to substitute this one here, then we can get f of z is equal to x plus iy, then we have the whole square, we have to expand it, then x square plus iy square, that is a minus y square plus I times of the 2xy. Here the real part is, u is equal to x square minus y square. The imaginary part v is equal to 2xy. Now we have to find the first order partial derivatives, dou u by dou x. Dou u by dou x is a 2x. Then dou u by dou y. Dou u by dou y is minus 2y. Then dou v by dou x, partial derivative for the second function. Dou v by dou x, derivative of this one with respect to x, 2y. Then dou v by dou y, 2x. Here dou u by dou x and dou v by dou y, these both are the same here. Then dou u by dou y is equal to minus dou v by dou x, that is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So that here we can say the real and imaginary parts of the functions satisfy the Cauchy-Riemann equations, as well as the first order partial derivatives dou u by dou x is equal to x, dou u by dou y is equal to minus 2y, dou v by dou x is 2y, dou v by dou y is 2x. These four first order partial derivatives are continuous everywhere, so that we can say the function f of z is equal to z square is analytic everywhere, so that we can say the function is entire function. Are you understood? Or you want to check the given function is analytic or not? First, we have to find the real and imaginary parts of the function. After that, we have to find the first order partial derivatives. After that, we have to check the Cauchy-Riemann equations are satisfying. Then, as well as the first order partial derivatives are continuous. Suppose the function is analytic function, then it should be satisfies the Cauchy's Riemann equations, as well as continuous PD means the first order partial derivatives are continuous. If the real and imaginary parts of the function satisfies Cauchy Riemann equations and the first order partial derivatives are continuous, then the function should be analytic. Then coming to the second problem, here we have the z square. We have to consider function f of z is equal to given function z bar. Since z is x plus iy, everybody know this, its conjugative is z bar is equal to x minus iy. We have to substitute this one in the given function. Then f of z is equal to x minus iy. Here the real part is x. Here the real part u is equal to x and the imaginary part v is equal to minus y. Therefore, dou u by dou x is equal to 1. Dou u by dou y is equal to, it does not contain the y, so that is a 0. Then dou v by dou x is equal to 0. Then dou v by dou y is equal to minus 1. Here dou u by dou x is not equal to dou v by dou y. Dou u by dou x not equal to dou v by dou y. Here u and v are not satisfying the Cauchy's Riemann equations. We know the Cauchy's Riemann equations. Dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. Here the first condition is not satisfied here, so that here the function f of z is not analytic everywhere. Since u and v are not satisfying the Cauchy's Riemann equations at each and every point, so that we can say the function is not analytic everywhere. Then coming to the second problem, e power z. Similarly, we have to verify this function is analytic or not. First, we have to consider the function. Consider the function f of z is equal to e to the power z. Since z is equal to x plus iy, we have to substitute there. Then we can get f of z is equal to e to the power x plus iy. Everybody know e to the power a plus b is equal to e to the power a into e to the power b. According to that principle, we can write the e to the power of x into e to the power iy. Everybody know e to the power I theta, that is e to the power I theta is equal to cos theta plus I times of the sin theta. So that according to this principle, we can write the e power iy is a cos y plus sin y, I times of sin y. Then this is equal to e to the power of x into cos y plus I into e to the power of x into sin y. Here e to the power of x into cos y is a real part. This is a real part. This is a imaginary part. So that here we can write u is equal to real part e to the power of x into cos y, and the imaginary part is e to the power of x into sin y. Now we have to write the partial derivatives for these functions with respect to x, then with respect to y. Dou u by dou x is e power of x into cos y. Derivative of e power of x is same as the e power of x, so that we got the dou u by dou x is the same as the u here. Dou u by dou y is derivative of cos y is a minus sin y, so that e to the power of x into sin y. Now we have to find the derivative for the second function with respect to x. Dou v by dou x e power of x into sin y, then dou v by dou y, derivative of the sin y is a cos y, so that e power of x into cos y. Here dou u by dou x is equal to dou v by dou y, that is dou u by dou x is equal to e to the power of x into cos y. Dou v by dou y is also same, e to the power of x into cos y, and dou u by dou y is equal to minus of this these are satisfying for all the values of x and y, so that the function exponential function e power z is analytic everywhere, so that it is also entire function. Then coming to the next one, sin z. Yeah, we have to consider f of z is equal to sin z, since what is the z? X plus iy. We have to substitute here, then we can write the sine of x plus iy. Everybody know here sine of a plus b, sine of a plus b is equal to sine a cos b plus cos a sine b. Now we have to apply this principle to this, then we can write sin x into cos iy plus cos x into sin iy. Then sin x into cos iy, we know cos I theta is equal to cos h theta, and another formula is sin I theta is equal to I times of the sin h theta, so that cos iy is equal to, according to this we can write cos hy hyperbolic function plus cos x as it is, sin iy, sin I theta is I times of sin h theta, so that according to that principle sin iy is, we can write the I times of the sin h y, so that here the real part is this, and this is the imaginary part. Here the real part is u is equal to sine x into cos hy. Imaginary part v is equal to cos x into sine hy. Now we have to write the partial derivatives to these both functions. Dou u by dou x, derivative of sine x is here cos x into cos hy as it is there. Then dou u by dou y, derivative of the cos hy is the sine hy, sin x into sine hy. Then dou v by dou x, derivative of this function with respect to x, derivative of cos x is minus sin x sin hy as it is, dou v by dou y. Now we have to write the derivative of the sin hy. Cos x is treating as constant, it is as it is, cos x into cos hy. Here these both are the equal. Dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus of this, so that u and v are satisfying the Cauchy-Riemann equations. Here dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x for all the values of the x and y, as well as the first order partial derivatives are continuous. Dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, all are the continuous. Dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y are continuous for all the x and y. Therefore this function sin z is analytic everywhere, so that it is also entire function. Then coming to the second problem, here we have the z into z bar. Consider f of z is equal to z into z bar. Everybody know z into z bar is mod z square, and everybody know z is equal to x plus iy. Z bar is conjugative of the z, x minus iy. We have to write the product of the z and the z bar, then we can get the mod z square. That is here x square plus y square. If you are multiplying the z and the z bar, then we can get this one. You know, a plus b into a minus b is a square minus b square, so that here z into z bar is x square minus iy square is minus y square, minus into minus plus y square, so that we can get here x square plus y square. It does not contain the imaginary part, so that we can write the I times of the 0. Here the real part is this, the imaginary part is 0 here. So that here we can write the u is x square plus y square, imaginary part v is 0. Now we have to write the derivatives. Dou u by dou x is 2x, dou u by dou y is 2y, v is 0, so that here dou v by dou x is equal to 0, dou v by dou y is equal to 0, since the imaginary function is 0 here. Right, here dou u by dou x is equal to dou v by dou y at the origin, I mean at the point x is equal to 0. Dou u by dou y is equal to here minus dou v by dou x only at the origin, so that here this function is differentiable at the origin. Now first I am writing the CR equations. Therefore dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou y only at origin 0, 0. That means the function z into z bar is differentiable at origin, but not differentiable at the surrounding points of the origin. Here I am writing the origin here. This is a 0, 0. This function is differentiable only at the origin. It is not differentiable in this neighborhood, so that here this function z into z bar is not analytic everywhere. Coming to the in the previous problems, there the real and imaginary parts u and v are satisfies the Cauchy-Riemann equations. At a particular point and as well as around the surrounding points. That's why there we said the functions are the analytic, and we proved that functions are entire functions. But coming to here, this function is satisfying the Cauchy-Riemann equations only at origin, so that we can say it is a differentiable only at origin, not differentiable around the neighborhood of the origin, so that we can say this function is not analytic at origin and not analytic everywhere. Then coming to the next problem. In this problem, directly they given the what are the real and imaginary parts. Here the real part is x square minus y square. The imaginary part is minus 2x y. Now we have to write the derivatives. Dou u by dou x is a 2x. Dou u by dou y, its a derivative with respect to y is minus 2y. Then coming to the derivative for the second function, dou v by dou x is minus 2y. Then dou v divided by dou y. Dou v by dou y is minus 2x. In the Cauchy-Riemann equations, the first condition is dou u by dou x is equal to dou v by dou y. But here dou u by dou x is 2x, but here minus 2x, not satisfied here, not satisfied. Therefore here Cauchy-Riemann equations are not satisfied, so that this function is not analytic. Then I gave the few worksheet problems. You have to practice them. Then you can able to solve any problems on the analytic function. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.